Alright class, so I gave you a few practice problems to do. We're done with this chapter. We talked about Lewis structure. When you have a covalent compound, they're sharing an electron. Lewis dot structure is a way to show the bonding, how they're sharing the electron. We talked about Vesper geometry, which is the geometry of covalent compound, and the way they put it together, they put the atoms to be as far away as they can from each other. And then we talked about polarity, how electrons are distributed in the molecule, and the hybridization. Now, let's go over this practice problem. Hopefully, after going over this practice problem, you're going to get down all these concepts. So, xenon F2 was the first one. And if you remember, we said the first thing that you do, you count the number of valence electrons. Because valence electrons are involved in bonding. Xenon fluoride has 22 valence electron. Okay, and again, we said that valence electrons are far away from the nucleus. They can't really feel the plus charge, so they can play around. They're involved in bonding. Other electrons are not involved in bonding. And we said the least electronegative atom usually goes in the middle, and that's usually the first atom. Usually the first atom goes in the middle, which is the least electronegative atom, except hydrogen. Hydrogen will never go in the middle. So here's xenon, and then I have I'm going to put the two F's around it. And then we said draw a bond between the center atom and the surrounding atom. Okay, now each covalent bond, what does this keep happening? Each covalent bond has two electrons, right? Each covalent bond shares 2 electrons. So how many have I already put down? 1, 2, 3, 4. So I've already put down 4. 22 minus 4 is 18 electrons left to account for. Then we said, look at the surrounding atoms first to see if they're happy. If not, they're not. Let's make them happy. Is F happy? F is not happy. It has only 2 electrons. It needs 6 more to be 8, because we said having 8 valence electron is considered very sexy in chemistry, because they want to have an octet to look like a noble gas. The same as this F. So each F has only 2 electrons. We add 6 more to make sure they have 8. This one is happy. This one is happy. So how many did we add? We added 12. Now we have 6 electrons left. What am I going to do with the 6 electrons? I'm going to add it to the center atom. 1, 2, 3, 4, 5, 6. Okay. Now I have no electrons left. Now I have no electrons left. So far, so good. All right. So here is my compound. So as we said, F is happy. F is happy. Is xenon happy? It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It is more than happy. It has 10 electrons, and we said it's okay to have more than 8 as long as you're not on the second row of the periodic table. What is the geometry? Here's the Vesper geometry. What is the geometry? The geometry is linear. The geometry is linear because you have a center atom, 3 lone pair, and 2 bonds. So the geometry is linear. Now, is this polar or non-polar? Is this polar or non-polar? I give you a little shortcut. I said these geometries, the one that I'm circling, these are non-polar geometries. Except, there's one exception. Every time you have more than 2 types of atoms, it doesn't matter what the geometry is, it will be polar. But beside that, these are non-polar geometries. Okay, is linear one of them? Linear is one of them. So this is a non-polar geometry. And that means the electrons are distributed pretty evenly. I have some over here, I have some over here. They're distributed pretty evenly. Now, the last thing to do is hybridization. I even give you a shortcut for that. I said, remember, we have 1 s orbital, we have 3 p orbitals, and we have 5 d orbitals. Then count how many things you have around the xenon, because I want hybridization for the center atom. Watch over here. 1, 2, 3, 4, 5. I have 5 things around xenon. 1, 2, 3, 4, 5. So I'm going to go 1, 2, 3, 4, 5. sp3d is the hybridization. sp3d is the hybridization. So far, so good. Okay, nice job. Let's go to the next one. Next one is BrF5. Let me go a little faster now. Number of valence electron. Hopefully you got this right. 40. Let me see. Is 42 valence electron. Okay. Now what I'm going to do? I'm going to do Br in the middle. And I'm going to have 5F around it. At the beginning, it doesn't really matter what the geometry is or how you put it. Just put it around it. And then after that, you can figure out the geometry and see how it's supposed to be. Okay. Now, we said that each covalent bond is sharing 2 electrons. So how many did I already put down? I've already put down 10. Because again, valence electrons are involved in bonding. So what I have 32 electrons left. Now we have to make sure our surrounding atoms are happy. All these surrounding atoms, which are the fluorine atoms, each one has only 2 electrons. So each one needs 6 more electrons to have an octet, to be 8. So each one has 2 and it needs 6 more. Okay. Now I added 6 more to all of them. Now all the surrounding atoms are happy. Each one has 8. So I added 30. I have 2 electrons left. Okay. Where does that 2 electron is going to go? That 2 electrons left is going to go on the center atom. Okay. I want to do -2 here, so I have nothing left. So then I have nothing left. Is my center atom happy? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 is extra happy. So now everyone is happy and this is my compound. Now I talked about this before, but I want to talk about it one more time because now that we've done more practice, it's good to repeat things a few times. Why is it okay for Br to have more than 8? Remember this. Everyone wants to have 8 electrons, but it's okay to have more than 8 as long as you're not on the second row of the periodic table. Now, why is that? Here is why. It goes back to these energy levels. If you remember, the first energy level has S, the second has SP, the third one has SP and D. So when you are on the second energy level, S has 2 max electrons, P has 6 max electrons. So the max you can have is 8 electrons. But when you come to the third row, you have the 2, you have the 6. Now you also have the empty d orbitals, which you could have 10 more because the max you can have is 18, right? So even if you're not using it, you have the option of these empty d orbitals. So it's okay to have more than 8 as long as you're not on a second row of the periodic table, because the second floor, max is 8. There's no way to put it. Okay, so everyone wants to have 8. It's okay to have more than 8 as long as you're not on the second row. So here is my geometry. What is the geometry? What's the name of the geometry? The name of this geometry is square pyramidal. Square pyramidal. In a second, I want to show it to you. Square pyramidal. Okay. Is this polar or non-polar? You know the shortcut. This is not circled. So this is a polar geometry. Again, what does it mean to have a polar geometry? That means the electrons are not distributed evenly. You have more electrons on one side and less electrons on the other side. Now, let's do the hybridization. Again, remember, you have S, P, 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 D, 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 and D. How many things are around Br? Watch not my hand, this is my pointer. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I have 6 things around it. 1, 2, 3, 4, 5, 6. So I have sp3d2. That would be my hybridization. All right, nice job. Ready to do next one? Next one is a good one. Next one is HCN. Next one is HCN. Okay. HCN, number of valence electron is, it has 10 valence electron. Now, carbon has to go in the middle. And the reason that carbon has to go in the middle is because we said the least electronegative atom goes in the middle. That's usually the first atom, excluding hydrogen. Hydrogen could never go in the middle, so carbon goes in the middle. Now, how many have I already put down? Each covalent bond has 2 electrons. So I've already put down 4. I have 6 electrons left. Let's make sure surrounding atoms are happy. Is hydrogen happy? Hydrogen is happy. Hydrogen is not greedy. Hydrogen is happy with 2 valence electron. And boron, another exception, is happy with 6 valence electron. These guys, not greedy. Hydrogen is happy. Nitrogen, not so much. It has 2. It wants 8. So I need to put 6 more. So it would have 8. Okay? Now, my surrounding atom's happy. I have no more electrons left. Let's go to my center atom. Is carbon happy? Carbon is not happy. Carbon has 1, 2, 3, 4. Carbon only has 4. Now, how many more does it need? So I'm going to make sure you really understand this. Right now, it has 4 electrons. It needs how many more? It needs 4 more electrons, okay? So carbon has 4 electrons. 1, 2, 3, 4. It needs 4 more electrons. This is an arrow. It's not a weird looking happy face. If you need 4 more electrons, how many bonds is that? Remember, each bond has 2 electrons. So if I need 4 more electrons, I need 2 more bonds because each bond has 2 electrons. Now, I have no more here. We said when the center atom is not happy and I have no more electrons, I have to make double bond or triple bond. I have nothing from hydrogen to make a double bond or triple bond here, but I have a lot of these things on nitrogen, electron on nitrogen, to make those bonds. I need 2 more bonds, right? Because I need 4 more. I know I made a typo in one of my Lewis structure. I'm going to make sure I don't do the same thing. So, carbon here, bonded to hydrogen that doesn't change. We had this, that's still good. Now, I have 2 more bonds. This was here. Now I have those and then those one. Okay. Now I have a triple bond. Now I have a triple bond. Now, is everyone happy? Yeah. Carbon has 1, 2, 3, 4, 5, 6, 7, 8. Carbon happy. Hydrogen happy. 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen happy. What is my geometry? My geometry is linear. So when you have double bond and triple bond, that's not going to affect the geometry over here. It does affect the bond length, but it's not going to affect these geometries. Okay. Now, let's go over polarity. Is it polar or non-polar? Linear is a non-polar geometry, but we said that geometry doesn't matter. As long as you have more than 2 types of atom, you will always be polar. Is that the case here? Hydrogen, carbon, nitrogen. I have more than 2 types of atom. Because when you have more than 2 types of atom, there is no way they can cancel each other out. Just no way. You can only have 1 best friend. You can't have 2. If you do, it's going to be a disaster. Same idea here. So, nitrogen is pulling the electrons this way. I have more electrons on this side of the molecule than the other side. So it's polarized. It's polar. Now, last thing, hybridization. Last thing, hybridization. Okay, hybridization. Now, hybridization, again, don't forget that we have S, P, 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 and then D, 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 and D. All right, what I said before, I said double bond, triple bond, single bond, lone pair count as 1. So I want the hybridization for carbon. 1, 2. 1, 2. Because I have 2 things around the carbon. Triple bond, double bond, they count as 1. Single bond counts as 1. So 1, 2. I only have 2 things around carbon. 1, 2. Double bond and triple bond, they count as 1. So the hybridization is SP. Hybridization is SP. So far, so good? Okay. Nice job so far. Now, there's one thing I want to teach you here because I haven't talked about it, and you need to notice. And that is, and this is going to be a little bit side note, sigma bond and pi bond. How many sigma bonds and pi bonds do we have? Sigma bonds are basically your single bond. They are the foundation that you put down. So HCN has 1, 2 sigma bond. So the way I look at sigma bonds, those are the foundation. The first line you put down. Now everything after that is a pi bond. So 1, 2. The foundation is 2. We put down 2 bonds at the beginning. That's 2 sigma bond. Pi bond is everything after that. So 1, 2. I have 2 pi bonds. I have 2 pi bonds. Now let's do a quick practice problem to make sure you really understand the sigma and pi bonds before we do our last take-home problem. CO2. Draw the CO2 for me. Okay. Now, do the hybridization for carbon atom. And how many sigma and pi bonds do we have? Pause my video and do this for me. Okay, now that you unpause me. First of all, the hybridization of carbon. What is the hybridization? 1, 2. There are 2 things around the carbon. 1, 2. There are 2 things around the carbon. This is for HCN. Okay? There are 2 things around the carbon because double bond and triple bond count as 1. All right. Now, how many pi bond and how many sigma bond do I have? Remember, the first one that you put down, the foundation, that's the sigma bond. I have 2 sigma bond. How many pi bond do I have? Everything after that, those are pi bond. I have 2 pi bond, 2 sigma bond, and then 2 pi bond. So far, so good? Okay. Ready to do the last one? Here's what's the last one. ICl4 minus. Now, if you add up all the valence electron, what you get 35 valence electron, except, what does minus means? Minus 1 means you have to add 1. So, 7, each one has 7 times 5, 35 valence electron. Minus means I have to add 1. So I'm going to add 1. If I do that, I get 36 valence electron altogether. Now, I is going to go in the middle. That part hasn't changed. And then I'm going to have Cl, 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 Cl. Draw a bond between the center atom and the surrounding atom. Now remember again, each bond has 2 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. I've already put down 8. 36 minus 8 is 28. I have to make sure the surrounding atoms are happy. Each Cl has 2 electrons, is not happy, and it's 6 more to be happy. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay? All right. Now, how many have I put down? So 6 times 4, I put down 24. I have 4 electrons left. Okay? So my surrounding atom, happy, 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 happy. 4 left. Those 4 left goes on a center atom. Okay? And then I have no more electrons left. Is a center atom happy? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Is more than happy, but it's not on the second row of the periodic table. So everything is good. Everyone is happy. Now, something a lot of people do, because this ends up being an ionic compound, since it has a charge, they put a bracket and they put a -1 charge outside it. Okay. What is the geometry? I have the geometry sheet right next to me so you can shout your answer. Your answer is square planar. Yes, square planar. Now, is this polar or non-polar? Now, here's where it gets a little tricky. When you have compounds that have a charge, like this one, then they just become ionic. So the polar or non-polar is not going to be relevant anymore. It's just become ionic. You have a lab on this, so remember that for lab, it just becomes ionic. Polarity is not going to have an effect. It's just going to become ionic because you have a charge on it. Now, hybridization. You ready for a hybridization? Again, S, P, 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 D, 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 D. Watch over here. 1, 2, 3, 4, 5, 6. I'm going to do it again. 1, 2, 3, 4, 5, 6, right? So 1, 2, 3, 4, 5, 6. SP3D2. Okay, that's gonna be our practice problem. Now I wanna give you 2 more before we go. So over the spring break, you guys can do this. SO3 minus 2 and SO3. These 2 are different. SO3, sulfur trioxide, that's a covalent compound. Now this one, a sulfide ion, this is a neutral covalent compound. This is a polyatomic ion. So what I want you to do the geometry and the polarity and the hybridization for each one. And I'll post a video to go over these 2. Okay, nice job guys. Keep doing practice problems. And this should help you for lab. Hopefully this is going to help you for lab too.